How about the bidirectional A star? It's almost the same as A star and bidirectional BFS. Only one thing I added was frontier set. So I have a frontier set from the start and frontier set from the goal. Because now my frontier has a tuple, like coast and start or coast start and path. So it is hard to find the goal. So in the goal test, I cannot just use a frontier. So I'm going to use a frontier set for the goal test. Then, because a frontier set is just a set, each time whenever I pop from the frontier, I can just subtract the node set from the frontier set. So in this case, I can save some time. Now, working with adjacent is the same as my regular A star. Just checking the goal test is different. Then one more thing we can think about is from the goal, what is the cost? When you calculate the estimated cost from the goal, you are supposed to calculate goal to the start. So your goal node, the second frontier, will start from the total heuristic cost started to goal. Actually, goal to start, the heuristic value will be stored. So goal is not 0 anymore. That is another change in the bidirectional A star. How about the tridirectional A star? Tridirectional A star, one of the easiest way is calling the bidirectional A star 3 times with a different combination of the series. Then you are going to find the minimum value, minimum sum of the 2 paths. Then you are going to return that. If I want to use the bidirectional A star inside of the tridirectional A star, we're going to see the final direction, final path will be drawn multiple times. So to avoid this part, you can change a little bit of the bidirectional A star. In the bidirectional A star, you are not going to have a draw final path. So instead of drawing inside of the search method, you can draw final path in the main method. So I added it here for the bidirectional A star. That's because I'm using the bidirectional A star in the tridirectional star. Then, because I'm using the bidirectional A star inside of the tridirectional star, tridirectional search, another problem happened. The window. So I want to draw the every 3. So all of them into one root. That means I cannot make tick-enter inside of the bidirectional. So if you see here, I did not instantiate tick-enter. There's no root here. Root is now passed as argument. Root and canvas you can pass to the bidirectional A star. That means you're going to make root inside of the main. So after you are done A star, you can just add those 4 lines in the main method and pass root and canvas to your bidirectional A star. Same thing. Tridirectional A star, you want to have only one window, one tick-enter window. So you are going to make the root again inside of the main before try search. Then you are going to pass the same root and same canvas to each search. So you pass a root and canvas to the tridirectional search. Then inside of the tridirectional search, you are going to pass same root, same canvas to each bidirectional A star. And one more thing I can say, this one is recalculating the path cost. If your path cost is off from the sample output, you can think about if you calculated correctly or not. Also, if your path length is too short or too long, you can also check if your previous path is the neighbor of the second path, or second path is the neighbor of the previous path. So if it is really connected by the neighbor by neighbor, you can also check it. So this is a kind of a hint for you how to check those. Then if I run it, I'm going to run from the Los Angeles to Miami and Chicago. It's a third city. This is the BFS. It is searching every 1,000 counter. Then when you see the result of the BFS, you are going to see it's going to returning the shortest path. That means length of the path is short. It does not count, it does not check the distance in this BFS. So you can think about there are two ways to find the optimal solution. This is the by BFS starting from the each end with the green color, then expanding until it finds a final path. So when your BFS and by BFS has the same path length, you can think that is the correct. Each time when you run, if you have the same path length, like 254, that means it is correct. The path cost can be different because bidirectional BFS and BFS are looking for the shortest path length. Then there are multiple solutions. That's the reason. Then A star and bidirectional A star is the blue color and bidirectional A star is the orange color. You can see explored part is very small. Then tridirectional A star. In my run, tridirectional A star is pink. So you can see the pink exploring. Then if you see only one final path, it is now starting from the Miami and go to the Chicago, then go to the LA. If you see only one final path, that means you did it correctly. And now let's see the data. If I start from the BFS, path length is most important. There are multiple solutions, so path cost can be different each time. It is okay. But if a path cost is around 3240 to 3264, 65, that means you are in the correct range. Then time-wise, by BFS should be shorter than BFS. Now, A star and bidirectional A star. A star is finding lowest cost. So when you find the lowest cost, 2711, that is correct. Length of the path will be usually, it can be longer than the length of the path of the BFS and by BFS because A star's purpose is lowest cost. So both are optimal solution, finding shortest path or lowest cost. Then if A star and bidirectional A star has the same cost, that means it is correct. Also, bidirectional A star should take the shorter than A star. And tridirectional A star, Miami to Chicago, then Los Angeles, or Los Angeles to Chicago to Miami. The order is not really matter. You can just find the shortest path to visit all three cities. Then, if you get 3,352 miles around this number, that means it is correct. So this is about the Lab 6 Part 1 and Part 2 details.